This is a flow rate measurement problem, and they say air at 200 degrees Fahrenheit and 60 psia goes from a 4-inch diameter pipe to a 2-inch diameter throat of Venturi. And they also give you the mass flow rate of 0.52 pounds per second. All right, so I went ahead and calculated, based on these conditions, the density and the specific weight of the air. And then I also, in a lookup table, found the viscosity. So we got our fluid properties out of the way. So why do we need to do all of this? So the relationship with the Venturi, I'll go ahead and say, so we have our coefficient, our throat area, and then the square root of 2 times P1 minus P2 over density 1 minus beta to the 4th. Because this is the expression that we're going to be dealing with. So let's look at each of these terms individually. Beta, in this case, is the ratio of the diameters. So that's going to be 2 inches over 4 inches, so 0.5, so that's straightforward. Okay. Then what we need to find, or what we can find out, is the volumetric flow rate. The volumetric flow rate, in this case, is the mass flow rate, so m dot, divided by the specific weight of the fluid. So we have 0.52 pounds per second. That was a given in the problem. And then we also found from our calculations, the first stuff I wrote down, what the specific weight was. And then that gives us 2.11 cubic feet per second. All right, so we have that now. Next, we can find the velocity before it enters the Venturi. So this is before it gets constricted. We can find the velocity of that. So velocity, Q divided by area. So we have 2.11 cubic feet per second divided by pi over 4. And then the 4-inch diameter, we're going to convert over to feet. We will get 24.2 feet per second. All right, so far so good. So now that we have this information, we still need to find out what the coefficient for a Venturi is, and that is a function of Reynolds number. And if you refer to our notes, so we need to find the Reynolds number for our flow. So Reynolds number, rho v d over mu. All right, so we get 7.63 times 10 to the negative third slugs per cubic foot. So we got that. Velocity, 24.2 feet per second. Got that. Diameter, 4 inches, which will convert to feet. Fair enough. Viscosity, 4.49 times 10 to the negative 7th pounds second per square feet. All right. So that gets us, when we calculate that, 1.37 times 10 to the 5th. All right, so that's our Reynolds number. So the next thing we're going to do is figure out the flow rate, or I'm sorry, the Reynolds number Next, in order to find the coefficient, the appropriate value of the coefficient, we need to find the Reynolds number at the throat. So they use a little subscript D in our textbook. So we need to find first the velocity at the throat, at the minor d. So we're going to have our volumetric flow rate that we calculated, 2.11 cubic feet per second, divided by pi over 4, and then convert the 2 inches to feet. You will get, through this calculation, 96.7 feet per second. And then let's get our Reynolds number for the same, rho v d over mu, and I'll put that there. And then actually, not to get confused, I will put little d here as well. All right, so then we will have 7.63 times 10 to the negative third slugs per cubic foot times 96.7 feet per second times 2 inches converted to feet. Viscosity, 4.49 times 10 to the negative 7th pounds seconds per foot squared. All right. When you go through that calculation, you will get 2.74 times 10 to the 5th. So with that Reynolds number, let me go ahead and make that a little more clean. All right, so with that Reynolds number, you then look up, I'll put this on the next slide, the coefficient for the Venturi nozzle with that particular Reynolds number. There we go. That's the relationship that we're going to use. So 1.0054 minus 6.88 square root 2.74 times 10 to the 5th equals 0.99. And that's within the realm of what we would expect. So we have 0.99 there. And then we can start plugging into our primary equation. So we have the volumetric flow rate equal to our coefficient, 0.99, times the area at the throat there we have that, and then square root of 2 times our pressure difference, which we'll solve for that as a group, and then we'll figure out each one of these individually later. We'll get to that. And then 7.63 times 10 to the negative third slugs per cubic foot. And then our 1 minus our beta to the 4th. All right, we have that. So when we go through that calculation, you will get P1 minus P2 to be equal to 36.4 pounds per square foot. You can convert that over to 0.253 pounds per square inch. And then ultimately the question is asking what's the pressure on the other side, not what the pressure difference is, because you know that the input is 60 psia. So then you have 60 minus that difference will give us 59.75 psia for your answer.